Alright, so today I'm going to be talking about simple harmonic motion, which is a Unit 6 in AP Physics. So yeah, here we go. So as you may know, a spring that follows Hooke's constant is called an ideal spring, and we need that to exhibit simple harmonic motion. So well, let's first think about it this way. What is simple harmonic motion, right? So we can shorten it to SHM, simple harmonic motion. And basically, for something to exhibit simple harmonic motion, A, it has to be in motion. B, it has to be harmonic. It has to repeat. And C, it must be simple, which means the force that is attempting to restore the object to the equilibrium position is directly proportional to its displacement. So what exactly does that mean, right? So let's take our force of the spring, which, remember, the spring force is always a restoring force because the spring wants to return us to its equilibrium position. So if you know Hooke's law, this is true. The force of the spring is equal to negative k, which is spring constant. I should write that down somewhere. Equals spring constant. And this is given in newtons per meter. And this is given in newtons per meter of a spring, and then x is obviously the displacement from the equilibrium position. So if I just switch to my purple marker here, if we have this diagram here, and let's just call this middle position x equals 0, so displacement is 0 at the equilibrium, and then we have some maximum position that the block can be at, and we'll call this x maximum positive, and then there's some minimum position that the box can be at, which we'll say is here, which is negative x maximum. And let's just say we have our block here, there's some wall, and there's a spring that connects it like this. So if there was no friction, this was frictionless, no air resistance, no nothing. If you pull this spring to the x maximum position and you release it, it will oscillate between these two positions indefinitely in such a cosine wave fashion. So if you were to model this, if you wanted to model position, it would be a cosine wave. And this distance, I'm going to call the amplitude. So right here, I'm just going to call it A. Because if you take a look on a graph like this, it will look like this cosine wave. And we have our amplitude starting from here to here, or from here to here. So this will be A. And this is also A. Just for sake, it's slightly offset, but it usually should start right at the maximum position. And today I'm mostly concerned about finding a formula for the period. And period is one cycle. So it's not from here to here, it's from here to here and back to here. So for it to return to its starting position, this is the period. Like that. And that is denoted as t. So t is equal to the period. So you may be wondering, well, how can we find the period of this? And, well, there's a few formulas we first need to figure out. The first one is the Hooke's law right here. And then the second one is the formula for the potential energy in a spring. So that's given by PE of the spring is equal to 1/2 K x squared. And x squared is the displacement here. So A is the maximum displacement, but if the block was like here, this would be called x, like that, change in x. And this is a vector of the displacement. So we would have x squared. So this equation gives us the total potential energy in the spring. But if we want to find the mechanical energy of the spring block system here, we also need to consider what is the kinetic energy of the block. And that's given by Ke of the block is equal to 1/2 mv squared, right? So if this is the case, then what would the the total be, right? The total should be the sum of the two. But let's say we're at the very middle. If we're in the equilibrium position, so when at equilibrium, the potential energy in the spring is 0. So that means Ke makes up all of the mechanical energy. But what if it's at the very end, at either this amplitude or this amplitude here, are the ending positions? So in that case, it's all potential energy, right? So if I call this XA, that means these two values, both of which are in joules, these two values should be equal to each other. And I should mention that that is A squared. So from here, what does this give us? Well, obviously we can cancel out the 1/2, real nice and easy. And then we actually want to find, we want A over V, A over V. Is that correct? No, yes, we do want A over V. So we're gonna divide the K over here, and then we'll take a square root, and then this will be A over V. And this will be important in a second. So there's a lot of places that prove how you could find the period using some very simple calculus, but since this is AP Physics 1, I'll try to do this without calculus. So I want to give a small example. So what if you had a vertical bobber like this, and then there's like a spring, and the rubber bobber is tied to the end, and it rotates in some fashion like this. So if you swing it around and rotate it, does that exhibit simple harmonic motion? And at the core, that question is pretty stupid because obviously no, it doesn't. But what is interesting is if you just look at it head on from a one-dimensional standpoint. So vertically, or from the top down, it's a circular motion, right? And then like, let's say the bobber's here and then the center's here like this. The velocity looks like that, right? But if we look from a head-on position, so we're seeing it perfectly flat and vertical, we'll see the bobber go from this side and travel to this side and come back to this side. And what does that suspiciously look like? That suspiciously looks like the spring equilibrium we see up here, how it tries to move back towards the center. And the question is, does this exhibit simple harmonic motion? And the answer to that is yes, it does. But first off, we need to prove it because we can't just assume that, right? So if we take our circle here, our nice circle, and we draw it like this, if you recall back to our circular motion or uniform circular motion, you know that the velocity at any given point is given by velocity equals 2 pi r times the frequency. So if we want this to exhibit, or if we want to prove that this exhibits simple harmonic motion, we must prove the very first principle that I mentioned, which is that the force that is attempting to restore the bobber to the center position must be directly proportional to the displacement. So if we're just looking at the x-axis, that is actually pretty helpful, because as you may also recall, if you have like the bobber here during the rotation, the force that restores it in the x-axis is going to be a component of the centripetal force, because we are only looking at it in the x-axis, which is this axis here. Because when we look head on, we only see one axis, and we just see it go like this. And my hand is going in a circle right now, but if you take away all the depth, it looks like it's just going side to side in a harmonic motion. So we want to find what this force is and then take the component, because the component of that force will be the restoring force in the x-axis. So in this case, the equilibrium point is when x equals 0, which indeed it is. It is x equals 0. It's at the y-axis. So the force that pulls something towards the center, the centripetal force, is always given by force centripetal is equal to v squared over r, right? And also, we're going to use some trigonometry here. The displacement in the x-axis is given by cosine of theta, right? Which is this angle here. So the displacement of x equals cosine of theta times the length. And the length in this case of this string is actually our amplitude. Because if you think about it, the maximum distance, if this is our center bobber and it's rotating, the maximum distance it can be away is the length. And the maximum distance is defined as the amplitude. So I'm just going to call this A here. So we don't even need this R anymore because the R is A. So we're just going to go V squared over A as our amplitude like this. And this will make sense in a second. So if this is our restoring force in 2 dimensions, what is the restoring force in just the x dimension? If we only want to look at it on the x-axis, we need to find this line right here. And that's pretty simple. Just use some trigonometry here. So I'm going to switch the marker here. If this is what it looks like here, and we need to find this and this. So if we're like traveling in a circular path, right? And this is our force centripetal. This, which we'll call force of x, force in the x direction, is equal, if we just use the cosine right here, or theta. This is the same theta that is down here, because parallel, remember? So we have cosine theta is equal to f centripetal, adjacent over hypotenuse, my bad, f of x, fx, like this, over f centripetal. So, let's notice something here. What is displacement? Displacement is cosine theta, right? So, if cosine theta is right here, and we have our restoring force here, we can write it as f of x, or fx, is equal to cosine theta times, so this is just some scalar multiplication, as you can see. So, if force of x is equal to cosine theta times f centripetal, well, what is f centripetal, right? We want to make sure there's no other random variables in there. So, as we said, f centripetal is v squared over a. So we have times v squared over a. And as you may notice, this does prove that in the x dimension, if you're looking just head on, a bobber exhibits simple harmonic motion because the restoring force, which is fx, the restoring force, is proportional to the displacement. The displacement is exactly cosine theta times a. So we know that displacement of x, change in x, is equal to a times cosine theta. And we don't really need to go further than this because we've just already proved that these two things are, in fact, directly proportional. So now that I've proved that this exhibits simple harmonic motion, we can go back to trying to find the period of a spring or the period of something that exhibits simple harmonic motion. So if you want to find the period of this in just the x-axis, it's actually quite simple. Because remember, we already know that the velocity is equal to f, is equal to the frequency times 2 pi r. So if frequency is 2 pi r, or velocity is 2 pi r, my bad, times the frequency, like this. Well, what is frequency? Frequency, by definition, is equal to 1 over period. They're exact reciprocals of each other. So we already know that v is equal to 2 pi r over t. But remember, what was r again? R is this radius of the circle, right? But it's also our amplitude. So I'm just going to rewrite that as our amplitude because the amplitude is just the maximum distance, and that indeed is the maximum distance. So from here, we're just going to have to switch the t and the v here using some algebra. And this gives the period of something exhibiting simple harmonic motion in the x-axis is equal to 2 pi times a over v. But the problem is, what is a over v? Oh, wait, we know what a over v is. It's right here. So this gives us t equals 2 pi times square root of m over k. So for a spring in one dimension, just looking along it like that, horizontally, the period is given by t equals 2 pi times the square root of the mass divided by the spring constant. And this should make sense because if you think about it mentally, that if the mass increases on the end of a spring, the period increases too, right? Because the force is like more sluggish almost, if you think about it that way. And if you have a stiffer spring, because the larger the spring constant, the stiffer, quote unquote, a spring is, and the more the restoring force is, it'll have a shorter period because it wants to go really, really fast, right? Think of like those door stoppers that you kick and it goes playing. It has a high spring constant, so the period is low. But if you put like something really heavy on the end of that door stop and you kicked it, it would go like vroom, 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 vroom. So this makes sense mentally if you think about it. And next video I'll go over a pendulum, which is slightly less sense, but it still makes a good amount of sense. It just only works for a few applications. So thanks for watching, and hopefully this convoluted explanation was somewhat understandable, but I hope this was of some help to you, and this is how you get this equation, which is really important in physics and on the AP exam. So, yeah. All right, thank you.